what we've done last Wednesday. I'll also cover some new materials on shocks. You guys noticed that I posted your third assignment, homework assignment? Okay. So you also noticed that the deadline is a little bit different than in the past because I gave you all the way down, I think, to 11 p.m. that Friday to do it, okay? Because I know some of you like to procrastinate a little bit, so all the way to the end, spring break. So the reason for this is, I guess that will make you happy a little bit. So I'm going to be out of town next Friday, so there's not going to be a lecture next Friday. So I felt like it was kind of not super nice to have you turn it in before class, even though there's no class. I'll give you the whole day. And I have plenty to grade. So, so we'll do this next, again, Monday. We're going to start promptly. So make sure, I know it's going to be Monday, but try to arrive on time because we have the visitors from the Glass Packaging Institute. And I would really appreciate if you guys are showing up on time and are somewhat dynamic during the presentation and participate, answer questions. That'll be good.
Extra credit, right?
Yeah, extra credit. In my heart right here. Which are the most valuable extra credit. Good. Let's get started. Quick thing last Wednesday. What we did is basically establish sorry, I get distracted. So we went back to force vibration a little bit after what we've done to the exam and put into context what happened in real life system where you have dampening, okay? And what does it implies for our packaging application. So what we talked about is we kind of went back to the same process, like baby step, what we did with vibration. We looked with free vibration with dampening and then forced vibration with dampening, and we looked what was happening, okay? So I'm going to go quickly here. So we introduced dampening. We look at the natural frequency for a free vibrating system with dampening. We had this term here that showed up, a little bit different, okay? We looked at how the system would behave depending on the dampening in that equation. And we looked at, for our interest, okay, I guess for mechanical engineers, what you don't want is vibration, right? If you have a dampener, you want to avoid this. You want the system to go back to equilibrium as soon as possible. So you try to aim, I guess, that was when I was doing that stuff a long time ago, okay? You try to reach critical damping, where you can go back to equilibrium as fast as possible. That's what the dampener should do on a car and things like this. So over damping takes more time to get to equilibrium, but when you are in that situation, this is where you have vibration. And for us, this is our interest, okay, is you see, you still have obviously a frequency with that vibration that is damped out with time, okay, but the difference between the natural frequency equation we used in the past and the one associated with dampening is quite small. That's the thing the takeaway from these. Now we went for force vibration, and I don't know if you remember, but when we looked at undamped force vibration and we looked at the input of the system and the output we were getting by the solution, we actually derived the equation for the magnification factor that links again that input and output. So if we perform that same exercise here, okay, you get a more complex solution, okay, and that graphical representation that is important, okay, is done here for various ratio, okay, of the critical damping and the damping factor. And what you see, okay, is what we mentioned before. If the force frequency is close to the natural frequency of your system, okay, you still have resonance, okay, when that ratio is 1. It's just now that it's obviously finite, okay? So that means, in a way, that what we're doing, okay, is a good approach to find out if we were going to be dealing with resonance or not. But the idea is that to understand that the resonance, if it occurs, is not going to result in an infinite output. It's going to result in a finite output. But basically, the magnification factor we used before will, in a way, tend to overestimate the output. So may lead to over packaging. But obviously, with testing and so on, we should be able to remove this and make use of the simpler calculation for our system. So we can go through this. You guys can go through this. Then we talked about vibration sensitivity and how it was important to look at it at the product level, package level, and pallet level. Okay, and we also discussed the fact that cosmetic damage is not. It's also important. Finally, we introduced random vibration. I don't want to talk too much about this. The idea is we are able to analyze or recreate those complex waveforms, okay, and put them into a power dense spectral density. And again, if you use a vibration table, that's what you're going to be seeing, okay? And you're going to learn more about this in your homework assignment. There's 3 papers to read, okay? So some are pretty short, some are a bit more extensive and a bit more complex, but they're going to talk about these things in your papers, okay? And one thing that also is going to be discussed in your homework assignment, and it's important, is that these tests are typically run for a short period of time. And when I say short period of time, it's about, ASTM is about 3 hours. It's not about, it's 3 hours, okay? So the idea is that some people like to say, okay, that performs well for me, I run the test, and it really shows up when I see the distribution environment, and the results I get from this are applicable, it works for me. Other people don't believe necessarily in these, and rather basically collect data, okay, on their truck, monitor their vibration, the acceleration, reproduce that on the vibration table, and shake it for whatever time your real shipment is going to go. So if it goes for 20 hours, you're going to shake it for 20 hours. So in a way, what standards procedures coming from ASTM and ISTM are doing, ASTM and ISTA are doing, they're doing what's called accelerated testing, okay? Like some of you may have learned about accelerated aging, when you expose parts, for example, polymers or other things, to higher temperature for a few hours to simulate years of use, okay? So it's a little bit similar. So that's the thing I want you to learn about, okay, and discuss through your homework assignment. Good. So that's what we discussed and did last time. Today we actually are jumping, okay, into shocks, okay? So that's the second and last part of last section that we're going to cover for the semester. So what is a shock? So the proper definition here is a shock may be characterized by a large and rapid increase in acceleration followed by a rapid decrease in acceleration over a short period of time, okay? So how short is that time? Typically, shock duration will be ranges between 1 and 50 milliseconds, and you're going to have a magnitude of magnitude with like 150 G. So when we come back from the break, actually, we'll go in the lab and we'll set the shock machine, okay? And I'll illustrate different impacts that we'll see, okay? And we'll talk about, we'll see how many G's, what it represents physically, and so on. So, in order to assess damage done by a shock, 2 of the 3 factors below must be known in a way. They're all linked together, okay? Peak acceleration is going to be 1, the duration of the impact, and also the velocity change, okay? They all link to each other, because if you know 2 of them, you know the third one, okay? In a way, if you have the graph of the acceleration over time, and you do an integration, okay, it gives you the velocity change. So the area under the curve, we're going to see that a little bit later, corresponds to the velocity change, and that is linked to the energy of the shock itself. Okay. So the next series of slides, okay, we're going to cover that and make use of that quite a lot for cushion design as well. So what type of shocks you may be seeing in the lab? Most of them will be seen in the lab. Okay. So on a shock machine, you can create different ones. You can create something that looks like an half sine type of impact, a trapezoidal or square impact. These might be a little bit more tricky to create on a shock machine. Ours will not do that. Okay, but these are different types of shock impact you can create. The thing is, for most packaging application, if you were to measure acceleration and measure an impact, what you will see is that the real life impacts are going to be half sine, okay? So they're going to look at half of a sine wave. You guys understand what I mean by this, right? So a sine wave does something like this, okay? So half sine means it's just looking like something like this. And we'll see as well, since the area under the curve here, okay, is associated with the velocity change, and I told you as well, it is associated with the energy of the impact. These trapezoidal types of impact, okay, for a certain maximum acceleration, will have a larger area under the curve, and therefore will be associated with more energy, and potentially will cause more damage than half sine shock for a certain peak acceleration and duration. Now, the energy that is actually gained or absorbed by the package, okay, depends, or it can be linked to what's called the coefficient of restitution, little e, okay. It is the absolute value of the ratio between the rebound velocity to the impact velocity, okay. So your product, if it falls on the ground, okay, when it falls, it's going to bounce back, okay. So most of the product, okay, some product don't bounce back at all. So the value for the coefficient of restitution can take any value between, I should have changed that, between 0 and 1, okay? So that means if you're dealing with something, for example, like a bag of something, okay? It can be like a bag of seeds or something like this. If it falls on the ground, most likely it's not going to rebound. It's going to fall and going to stay there, okay? So that means, okay, the rebound velocity is going to be 0, okay? So the total velocity change, okay, associated with something like this would be only equal to 2gh. What is this guy? Remember?
Max drop velocity or something like that?
The impact velocity, right? So it's coming down at an impact velocity, right? No, it's coming down and accelerating, and at impact, it's reached the impact velocity. And if it doesn't move back up, okay, that means the total velocity changes the impact velocity minus 0. So that's what you get there. So the opposite case, if again it's utopic, it's not going to happen. If you have an object that comes down and goes back up as fast as it came back down, okay, you're going to get therefore 2 times the impact velocity. So that's why I should have here, this thing here should be smaller, okay, because in real life we're not going to see this. So the ratio typically for most product is going to be between 0.3 and 0.5. That will be the coefficient of restitution. Now, to really get an understanding, okay, of what happened during the impact and what parameters influence, for example, the maximum acceleration and so on, we need to look at the physics of an impact, okay, and look at an energy balance, okay? So, if you think about this, what we will be, let me ask you this. So, let's say you were to, design or pick a cushion to protect against an impact. That's what we want to do, right? So, what are the things you may be interested of knowing if you were to perform a test and try to protect an object? What are the parameters or things you would like to know in order to really protect your product correctly?
The natural frequency of the product?
The natural frequency may actually will play somewhat of a role, okay? But we'll talk about it later, yes. Yes.
How thick, how much material I have to use?
Okay, the thickness is good, okay? And in addition to this, when it's going to impact, what's going to happen to that material? It's going to compress. So you're going to want to find how much you need, okay? We're going to do that later. We also want to find how much is going to deflect, okay? And that's the important part because some material have a certain working length, okay? At some point, when they compress it too much, it just becomes hard, okay? They don't compress anymore. So the working length is going to be important, and therefore the maximum deflection, okay? That's going to be important. What else?
Magnification factor?
You are going the right way, but it's a little bit different. So we're going to talk about, because an impact, if you think of it like this, it's like a very short vibration, right? So the natural frequency, okay, partially for components and things like this, may translate to a different shock that will be felt by a component inside your product, okay? And we're going to use something similar to a magnification factor. It's called an amplification factor in there. But one other aspect that it will be important, okay, and you probably agree with me, maybe it's just too trivial, is the maximum acceleration, right? We should know what will be the maximum acceleration that our product or object is going to feel, okay? So these are things we're going to try to work towards. So in here, what we're going to do, okay, is look at a free-falling object, okay? There might be cases where somebody throws a package, but obviously we're going to assume it's not going to happen here, okay? We're looking at free-falling objects. So a quick review, okay? A potential energy, okay, of an object, okay, exposed to to gravitational acceleration is expressed by the product mgh, okay? The mass of your object, the gravitational acceleration, and the height from which it's going to be dropping, okay? So the higher the drop height, the higher is going to be the potential energy. The kinetic energy is associated with movement of your object. It's linked to its velocity. The equation for the kinetic energy is 1/2 the mass times the velocity of your object squared. And for free-falling objects, we know that if it starts at a zero velocity and it's accelerated by the gravitational acceleration, what's happening is its velocity increases, okay? And it's going to increase until it hits the ground, okay? But throughout this, what we see is we have conservation of energy. Obviously, we neglect any drag and stuff like this, okay, for the velocity we're dealing with. So what we have here is the change in potential energy, okay, as it progresses is going to be equal to the change of the kinetic energy as it goes from zero velocity to impact velocity, and as it goes from a height of h to a height of 0. So the idea here, therefore, means that at the point of impact, all the potential energy has to be converted into kinetic energy, okay? So if you look at this, the kinetic energy at impact is going to be 1/2 the mass times the impact velocity squared. So if we do that, okay, we replace it to that equation, what we find, okay, if we raise that to if we square the square root here, the square root goes out, the 2 simplify, and we find that based on our basic analysis we had for the impact velocity, if you plug it in here, the physics holds, right? At impact, the kinetic energy is equal to the initial potential energy, mgh. Does it make sense? Good. So that's the first part here. Now, at impact, as your product falls onto a cushion, for example, that means that the energy associated with that impact has to be absorbed by the cushion, okay? Or the spring, if you want. Because remember, we treat those cushions as springs. So if you go back to your physics, okay, and you look at the energy associated with a spring, okay, you can basically integrate the force over a distance, okay, to find the work done by the spring, okay, which will be equal to the energy. So that equation here relates to the energy absorbed or provided by a spring. So 1/2 the spring constant times the displacement squared. So the thing is, your product is going to fall. It's going to displace the cushion, okay? and it's going to displace it in such a way, okay, that when it reaches the maximum deflection, that means all the energy has been absorbed. Does it make sense? So that's the reasoning behind it. Okay? And the maximum deflection, okay, all the energy of the product has been absorbed by the cushion, which means that, okay, right here, maximum displacement of the cushion, it must be equal to the kinetic energy at the impact, or if you want, the potential energy that was started all the process. So if we replace into those equations, what we can find, we find here, if we solve for delta max here, based on these two parts of the equation, we find an equation for the maximum displacement. I'm going to write this down here because we're going to need it a little bit later. Delta max will be equal to the square root of 2mgh over k. Good. So that would be the maximum displacement. Now, one thing that is also interesting is maybe to try to link that to other things, okay? For example, we mentioned that the maximum acceleration is something we are interested in. So we know that the force of a spring is given by Hooke's law, right? Minus k times the displacement, okay? If you look at this value, that the absolute value of this, we can find that the maximum force that the cushion or the spring is going to exert on your product when it reaches the maximum deflection is going to be equal to the stiffness of your cushion times the displacement, or in this case, the maximum displacement. If you do that, that means it's k times the maximum displacement we just described earlier. So you have k to the 1 here times k to the minus 1/2. So basically, you end up with that equation right here. Okay, the maximum force is going to be square root of 2mghk. Using Newton's law, okay, Newton's second law of movement, okay. So we know also that for any mass or any object, okay, the force is equal to the mass times the acceleration. And we also know that the maximum acceleration that will be felt by the product itself, it will be when its velocity reaches zero, when all of that energy has been absorbed by the cushion itself. So by doing this, if we equal the maximum force to that expression and calculate it, we end up with that equation right here. That will give us the maximum acceleration exposed by the product upon impact when you take into account the gravitational acceleration, the height of the drop, the stiffness of the cushion, and the mass of your product. So, before I jump to the next thing, let me write this down as well. We have this equation. So what can be done to rework this a little bit to make it, to link both of them together? And this is just a algebra trick, okay? If you take the maximum deflection, yes, of your cushion here, and under the square root, what you do is you multiply the numerator and the denominator by the same factor, 2gh. So that means you do not change anything to your equation, okay? In a way, you multiply the argument under the square root by 1. So if you do that, and you rearrange these terms together, you can notice that this is actually what we had just on the previous slide, okay? But squared. So this is 1 over the maximum acceleration squared. And regrouping this, what you see is you end up with the product of 2gh with itself on the numerator, and this, so that becomes 2gh squared. All of this under a square root. So that is the last equation here that links directly, if you want, the maximum deflection to the maximum acceleration. So this we're going to use a little bit later. Now, if you think about this, okay, the important thing as engineers, okay, is not just to look at an equation and say that's the equation, I have to use it and not worry too much about it. You have to think about it and try to think if it makes sense, okay? So in here, if you look at the maximum acceleration, Okay, you have to see, okay, it's proportional to the square root of the gravitational acceleration. I can deal with this. It's also proportional to the height, so to the square root of the height. So that means the higher the drop height, the higher the maximum acceleration. Does it make sense? Yeah. Okay. So the other term here in the equation is the property of your cushion or your spring. Okay. K, the stiffness of it. So what it means here is also indicates that the stiffer the cushion, okay, the higher is going to be the maximum acceleration. Does it make sense? Yeah. Okay. If you fall on a hard surface, you're going to feel a higher acceleration, and you're going to get more damage than if you fall on a softer surface. That makes sense. Here we have the mass. So that means here that if we have a larger mass, the maximum acceleration is going to be smaller. How do you make physically sense of this? Some people are scratching their heads. So an object with a higher mass is going to fall faster than an object? No, good. Most of you said no. That's good. Actually, have you ever seen that? There's a cool video. I think it was produced by the BBC or something, where they went in one of the super large vacuum chamber at the NASA and they redid the feather experiment, and it's really cool. You have I think they use like a bowling ball and the feather, so they make them fall with air, and then they pull a vacuum and they fall, and it's amazing. It really does. That thing moves, and it just contacts the soil at the same time exactly. So yeah, the mass is not important. So how can the mass here, you're dealing with the higher mass? And again, maybe you may want to think of it this way. Let's say you maintain all of this constant. So you have same drop height, same cushion, okay, you increase the mass. How come you will get a lower acceleration if the mass is higher? So let's think about this. Let's think about a feather, okay, falling on a cushion, okay? So it's going to fall. And what's going to happen to the cushion when the feather hits the cushion? Nothing, right? It's not going to deflect anything. So if you increase the mass, take different object slowly and slowly. If you have a very light object with respect to the stiffness of the cushion, when it impacts, okay, the cushion is not going to deflect, right? It doesn't have enough inertia. So that means falling, the relatively light object falling on a really hard surface or a cushion that is relatively stiff is not going to make any difference. It's going to have a very high acceleration. But as you progressively increase that mass, what's going to start happening, okay, is that cushion is going to actually do its job, okay? It's going to deflect, okay, upon impact, and it's going to absorb the energy, okay? And what that means, okay, you remember what acceleration is, right? If you look at basic, it's a change of velocity over a change of time, okay? So, the velocity change is constant, right? Because it goes from the moment it contacts the cushion from impact velocity, and it's going to deflect to a zero velocity. Okay, you agree on this? So, depending on how much the cushion deflects, okay, will adjust, play on the time, okay? So, if that deflection is pretty large, that means that the change of velocity is going to happen over a longer period of time, okay? And therefore, you're going to get a lower acceleration, okay? So, that's the physics behind this equation with the mass. That's what it means. I want you to be able to explain this, okay? If I were to ask you this question, okay, you should be able to understand why the mass is there and what it means physically, okay? And these statements or observation, okay, are important, and that's what we just discussed step by step. The maximum acceleration is related to the drop height, the characteristic of the cushion, and the mass of the product. So all of these statements relate to
these equations. Okay, partially this one. The stiffer the cushion, the larger the maximum acceleration. The higher the drop height, the higher the maximum acceleration. And the heavier the product, the smaller is the maximum acceleration. Assuming, this is important, assuming a well-designed cushion. What does that mean? What do you think that means here? So we just discussed that when you increase the mass, the cushion deflects more and more and more. So obviously, if you add such a mass that it just crushes the cushion, it doesn't do its job, right? So it's gonna bottom out. Okay, that's the expression we use. Okay, if the deflection is too large, at some point it's gonna go through. Okay, and then hit the hard surface. Okay, so in that case, what you may have, okay, is you may have a higher acceleration even if the mass increases back, because then we go out of the assumption that our cushion is not limited by its displacement, if you will. So that's very important. So few facts here about shocks, okay, that are been basically gathered through experimental data, observation, and so on. Okay, so the first one here is that the probability that packages will be dropped from a height greater than 1 meter is minimal. So obviously it varies, but 1 meter is about 30 inches. Okay, so that means that it's more than waist high. Okay, so that means that probability things are going to be dropped higher than this. It's not going to happen all the time. Okay, so that means it will have to be a package that's carried on the shoulder, or if it's on top of the pallet, it's going to fall. But most of the drops, okay, are going to be lower than this. So packages will also receive many drops from low heights, while few receive more than one drop from greater heights. So many drops from low heights, partially if you have mechanical ending system where you're going to have like drops, okay, or conveyor, and you're going to have the package are going to fall to different conveyor and things like this. You're going to have lower drop heights. Unitized loads are subject to fewer drops than you do individual package. That makes sense. If you put things on a pallet, usually if you drop the pallet from a truck, then it's catastrophic. That's not going to happen. But other than that, the chances that your box is going to fall off the pallet are pretty slim, unless it's not really well unitized, if you don't have stretch wrap or anything like this. So it's not going to happen as much as if you have loose items that are going to be carried and transported. This is something we already talked about, is that there's little control over drop orientation with small packages. With larger package, about half of the drops would be on the base, okay? So small package, people will put in different orientation and so on, and therefore they're going to be dropped in any types of thing. If the thing is heavy and large, okay, typically, if it's dropped, it's going to be on the bottom surface. So what do you think is worse? Is it worse to have a flat drop or drop, for example, on an edge or on a corner of a box?
Edge.
Who votes for edge? As a hedge for this? Edge. A few? Some are a little bit timid. Why do you think it's worse?
Crushes the ball.
Sharp edges.
Sharp edges
Worse or
crushes
better?
the box.
Worse or better?
I'm not going to tell you.
No, did your ask if it was worse or better?
Yeah, is it worse?
Oh.
Which one is worse? On the flat surface, or on an edge, or a corner? It's tough, right? In a way, it's kind of both, right? It depends what you're looking at. Okay, so if you have a drop on a corner, you're absolutely right. The corner is going to be crumpled, right? It's going to look terrible, okay, and it's going to be bad for the look of your box. Okay, partially that box is going to be displayed. So in that sense, it is worse. But for the product inside and for the acceleration level in the box, it's a lot better than if it falls flat. Okay, why is that so?
The corner is more reinforced than any of the sides, I guess.
Actually,
You get two cushions.
yes, in a way, the corner,
Maybe
unless
four.
it's such that you hit your object, but it's crumble, right? So it basically acts like a cushion. So it's going to deflect, okay, and absorb the energy, okay, and have basically a lower acceleration. If you have a flat drop, okay, most of the energy is like boom, okay, transmitted right away inside the box. So you're going to typically have higher acceleration level on flat surfaces, okay, than if you have it on a corner. So more heavier package has a lower probable drop height than a lighter package. So here I've added this here. This statement is disputed in the industry. Why do you think some people disagree with this? You think about this. Heavier box has a lower probable drop height.
Because people are less likely to bring it up so high if it's heavier.
Okay, well, that's good. But if it's really heavy, you know, if you try to carry it this way, it might be easier to put it on your shoulder, right? It's not a good, so that's one thing, okay? And if it's heavy, that means you're going to carry it with sometimes two people, okay? So if you don't have good communication, okay, drops me, you remember that the papers I have you read for your first homework, right? People dropped the chromatograph when they were carrying with two people. So that's one thing. So what else? What do you think some people may say that this is not true, that the mass is not really a factor here?
If it's heavy, it might not even be carried by humans, it might be carried by equipment.
Okay, that's good. So equipment-wise, okay, let's say most of these packages, okay, even let's say if it's 60 pounds, okay, usually 50 pounds is the threshold that it's going to require more than one person to handle it, okay, for, you know, prevent like professional injuries and stuff like this. So if your boxes go on conveyor system, okay, they don't know the weight, right? And every day, okay, there's boxes falling off on these conveyors, okay? So if it falls off of a conveyor, which is about a meter, you know, if it's typically waist high, okay, it doesn't matter the weight. So again, that's different argument, okay? You may also say that sometimes it links to this, okay? Handholds reduce the probable drop height by lowering the package relative to the ground. So if you have a heavy box, sometimes you will put handle on it, okay? And that means that instead of carrying your box from the bottom like this, okay, I would carry it maybe from here, okay, with the handles, okay? That means you lower the drop height, okay? That's a good thing. But also if the box is heavy, that might be one reason why you have drop heights as well. You have handles, okay, to facilitate the handling. Because if I remember correctly, I think putting handles on a package, okay, influenced the perception of you guys or everybody handling the box of the perceived weight, okay? It appears lighter, okay? I think it was like 16 or 20% lighter if you do a test, like a blind test with the same weight with handles or without handles, okay? So that means that if you grab a box, let's say you're a lumper in a way, so you're one of these guys that are in charge of loading and unloading these things. If your job is such that you cannot or you will not handle a box that is pretty heavy by yourself, let's say you grab it and you try to pull it and you just feel it's really heavy, you will drop it and you ask somebody to help you because that's how people work, I guess. But if you have handled, that means most likely people are not going to drop the box, okay? It appears lighter, it might be help to carry it as well. So this is things, and again, this is why I said that is disputed. Is really, again, some equipment don't discretize if it's, or discriminate if it's basically heavy or not. Conveyor and so on, handles make sense. Cautionary labeling, we also talked about this. This side up, fragile, things like this. It has only a minor effect, okay? So it doesn't hurt to put it on. Obviously, it costs a few cents maybe. But it doesn't make up for something that is really light. And also, once again, mechanical handling system can take labeling into account. Not yet, actually, but even if it's fragile or something like this, people still gonna put it on conveyor, it may fall, okay? So it doesn't help too much. And you've seen as well, you remember in when we have some pictures for air transportation, if people have to fit the box into an aircraft container to maximize the load, if it has to be this way, even though it says this side up, they're going to put it this way. Okay? So as long as it fits, they're going to do it. So in here, what we have is different graphs that are coming from experimental data. So what we have here is drop height. Here the x-axis has a version of the number of drops for a 25 pounds fiber box, fiberboard box. And again, there was 15 test packets and of 80 trips, and they probably had a accelerometer in there that monitored it. So you see, for a 25 pound box, you have a lot of drops from low heights, okay, 6 inch or even a foot or less. And you have very little or few occurrences of very high drops. So that's one of the things we discussed. So you are likely to have many drops from small heights and a few drops from very high heights. In this case, this is one graph that tried to justify that statement that you're going to have higher drop heights for light package than for heavy package. So these lines obviously are the probability of these drops occurring, okay, with the product weight. And if you take time to look at this, okay, this is where you see that light package, you're going to have more chances to get higher drop height. And as it was mentioned by Alex a bit later, at some point it plateaus because when you start dealing with 65, 70 pound types of package, okay, things are going to be handled mechanically, so it's going to flatten out on the probability here. So what kind of fragility typically objects have, okay? So this is a table, again, you don't have to remember these, okay? But you get an idea about what type of maximum acceleration most or many appliances or objects will have in the distribution environment. So if you have, also it's mentioned here, if you have a product that has a fragility level less than 30 G, you may think of redesigning it. So precision instrument, okay. Obviously, computer hard drive, this should be redone at some point as well because more and more you have solid state drives and with very little moving parts in these equipment, so it's getting better, but this is just to give you an idea. I think I'm going to stop here before I go to the next slide. So, thank you guys for coming today. I will wish you a great weekend, and I will see you next Monday. So again, please arrive early as much as possible. I'm going to have guest speakers.